Hello, and welcome to G Fun Facts Online. 100 years ago, our understanding of the universe was shattered. A strange new theory called quantum mechanics was born, revealing a world at the subatomic level that was bizarre, probabilistic, and completely unlike anything we knew. As we approach the 100th anniversary of this revolution in 2025, we find ourselves in the middle of a second one. And just like the first, this new quantum revolution is fueled by a profound revolution in the one language that can describe it: mathematics. Today, we're diving deep into the new math that is reshaping our understanding of reality itself. The first quantum revolution in the 1920s was a messy, brilliant affair. Thinkers like Niels Bohr, Erwin Schrödinger, and Werner Heisenberg were trying to make sense of things classical physics just couldn't handle, like why electrons act so weirdly. At first, there wasn't one clear theory. Heisenberg came up with matrix mechanics, describing the quantum world as particles making discrete jumps, using arrays of numbers called matrices. At the same time, Schrödinger developed wave mechanics, which saw everything as waves described by his famous wave function. They seemed totally different. It took the genius of Paul Dirac to show they were two sides of the same coin, and later, John von Neumann gave the whole thing a rock-solid mathematical foundation. He established that the quantum world plays out in something called a Hilbert space, an abstract mathematical space where the state of a system is a vector, and things we can measure, like energy, are operators that act on those vectors. This was radical. It threw out the predictable, clockwork universe of Newton and replaced it with a world of probabilities and quantum jumps, all defined by complex and abstract math. For decades, this mathematical framework was astoundingly successful. It gave us lasers, transistors, MRI machines, basically the entire digital world. But big questions remained. We still can't unite quantum mechanics with Einstein's theory of gravity, and we still argue about what it all means. Now we're in what's called the second quantum revolution. This time, it's driven by technology. We're learning to control individual quantum systems, which promises things like quantum computers and unhackable communication. This new power is forcing us to rethink the math all over again. It's a new mathematical dawn, where physics and abstract math are merging in ways we've never seen before. So what does this new math look like? One of the most exciting ideas is that quantum mechanics might just be a manifestation of some deeper geometry. Researchers like Nima Arkani Hamed at Princeton are exploring this. He and his team discovered a geometric object they call the amplituhedron. This object provides a radically new and simpler way to calculate how particles interact, without all the usual complicated steps. It suggests that the complex rules of the quantum world might just be a shadow, a projection, of a simpler, more elegant geometric reality hiding underneath. It's like finding out the complicated rules of chess are just a consequence of the simple geometry of the board. Then there's topology. Topology is the branch of math that studies properties of shapes that don't change when you stretch or bend them. Think of a coffee mug and a donut. To a topologist, they're the same because you can deform one into the other without tearing it. Physicist Edward Witten, who famously won the Fields Medal, math's highest honor, pioneered a field called topological quantum field theory, or TQFT. These theories have uncovered incredible, deep connections between quantum physics and pure math, like the study of knots. Beyond the abstract, TQFTs are now crucial for understanding exotic states of matter that could be the key to building stable, error-resistant quantum computers. The late, great mathematician Sir Michael Atiyah laid down the formal rules for these theories, giving us a powerful new toolkit. Finally, there's the lens of information. The rise of quantum information science has completely changed the game. By treating quantum mechanics as a theory of information, we're gaining new insights. It's helped us better understand spooky action at a distance, or entanglement, that weird connection between particles. This perspective is even being applied to the biggest mysteries in physics. Some researchers believe that the key to solving the black hole information paradox, what happens to information when a black hole evaporates, lies in understanding the flow of quantum information. There are even wild ideas that gravity itself might emerge from the patterns of entanglement in the universe. As we look back at a century of quantum mechanics, we see a story of an incredible partnership between physics and mathematics. Today, that partnership is stronger than ever. The second quantum revolution is pushing us into new mathematical frontiers. As the mathematical physicist Robert Dicroft puts it, there's an unreasonable effectiveness of quantum physics in modern mathematics. It seems the strange rules of the quantum world aren't just a description of reality. They are a source of brand new, powerful mathematical ideas. The journey that started with a few minds grappling with the subatomic world is now a global quest, promising to reveal even deeper secrets of the cosmos in the century to come. Thanks for listening to G Fun Facts Online.